Lesson 5.3, Graphing Radical Functions. In this lesson, we'll look at parent functions for square root and cubed root, and then we'll look at transformations. A radical function is defined as any function with a radical symbol. These functions will be nonlinear. Well, that's linear, sorry. Nonlinear and even functions, or even roots, will have restrictions in the domain. We'll start off by graphing the parent functions, and then we'll look at transformations. On the right, it says graph the following parent functions. State the domain and range. Is the function increasing or decreasing? The first function that we'll graph won't have a number in the radical or the root formula, or the root kind of location. This is called a square root function. Thinking about square roots that have actual values, the smallest square root that we can evaluate is plugging in x equals 0, because the square root of 0 is in fact 0. Anything less than 0 would not be a real solution. But if we plug in numbers on the right, positive 1, the square root of 1 is 1. So that works out just fine. The square root of 2 is approximately 1.4. So if we go 2 to the right, it's up just a little bit further than that. The square root of 4, if we move a little bit further, is a perfect square. That would equal 2 exactly. So a little bit higher up. The next perfect square that we could evaluate would be all the way over at 9. And the square root of 9 is 3. So over 9, up 3. What ends up happening here is that we start at 0, 0, because if we were to substitute in a negative value, that would not be possible. That should say not possible. So starting at 0, 0, we'll curve over through those points to the right, and as x increases, the values would also increase for the square root. That means our domain can be anything for x that is greater than or equal to 0. And if we plug in anything greater than or equal to 0 for x, our output would also be greater than or equal to 0. Our next parent function is the cubed root function. And we have a little bit more flexibility with this. Cubed roots can be positive or negative. And we'll plug in both kinds of values for our input. Thinking about our cubed column for our power chart, 0, the cubed root of 0 would be 0. Any root of 0 is 0. Now watch this though. If we pick a cubed root of 1, what number times itself 3 times equals 1? Well, that would be positive 1. So we plug that in on the right. But if we plug in negative 1, the cubed root of negative 1 is in fact negative 1. So it almost looks like it's going to be a straight line. But if we look at our perfect cube column, the next perfect cube goes all the way over to positive 8. And the cubed root of 8 is 2. If we go over to 8 and up 2, you can see how there's that non-linear shape starting to happen. If we plug in negative 8, we get negative 2. The cubed root of negative 8 is negative 2. So let's plug in something in between. Let's try 5. The cubed root of 5 wouldn't be something on our power chart. We'd have to plug it in our calculator. And the cubed root of 5 is approximately 1.7. If I go over to positive 5 and over 1.7, it looks like those points should connect from the middle of the graph over to that right-hand side. If we did the same thing with -5, we would get approximately -1.7. So -5 down to -1.7. This shape is going to kind of be like a flat S shape. As you connect it from left to right, it's going to connect through those points on that left-hand side, come up, and then connect over to the right forever. It should be more of a curved shape than what I have here. Just kind of hard to draw that in. So you can kind of see that weird shape starting to happen. Because there are arrows on both sides, the domain is unique here. The domain is going to be all real numbers. It can be positive or negative. And even though the graph doesn't get really, really big or really, really small for the range, the same rule applies for your output. The range can also be all real numbers. And those are the parent functions for square root and cubed root equations. What we'll do now is describe their transformations. As we describe transformations, we're going to look at the generic template y equals a times the radical or root of x minus h plus k. In this type of transformation, we'll look at the descriptions very similar to what we did back in quadratics with semester 1. The a value, or the number that's on the outside of our radical, is going to stretch or compress vertically. And these are all things you should be writing on that left-hand side. For some reason, I don't have that marked over here on my video, so we'll make sure we get those in there. If you have an h value, that's going to be on the inside with x, so it will move it right or left. And if you remember from quadratics, it always goes in the opposite direction from what the sign tells you it would be going. If you have a k value, that's going to move your graph up or down, and that moves up or down the same amount. If it's positive, it goes up, and negative, it goes down. Now, we'll also need to figure out when you have an nth root that's even, how to determine your domain and range. For your domain, anything that's on the inside with x, what you'll want to do is set that greater than or equal to 0, and then solve for x, and that will be how you determine your new domain. Values for x that will make that inside possible. For the range, you'll want to plug your x value back in, and that should help you determine your original output and then decide if they're positive or negative from there. All right, keeping that in mind, what we're going to do is bring this graph back up so that we can describe the transformation and sketch the graph for g of x. It says graph g of x equals 2 times the square root of x plus 3 plus 5. What transformations map the graph of f of x equals radical x to the graph of g? How do the domain and range differ? Well, let's look at starting to describe with our parent function. If we know that f of x equals radical x, we'll plug in the same points that we did up above. We'll have 0, 0, 1, 1, whoops, try that again, 0, 0, 1, 1, 2, 1.4, and then if you remember, we went over to 4, and the square root of 4 is 2. 9, the square root of 9 would be 3. And from 0, 0 over to the right, there's our parent function. Now let's take a look at our transformation for g of x. Whoops, let's get rid of that. I don't know why it's kind of like a highlighter. For g of x, we have a 2 on the outside, we have x plus 3 on the inside, and then 5 after. The 2, since it's greater than 1, means our graph is going to stretch. So it stretches vertically, which means as we go from left to right, the graph will get taller at a faster rate. The x plus 3 means h equals 3. And instead of moving 3 to the right, it actually is going to move 3 to the left. It always goes in the opposite direction. The 5 is on the outside, that's our k value. And if k is positive, it moves up. If k is negative, it moves down. So if k equals 5, we're going to move up 5 units. And then we need to determine our domain and our range. For our domain, if there's something on the inside with x, we follow the definition of setting that greater than or equal to 0. The inside is x plus 3. We will set x plus 3 greater than or equal to 0. To get x by itself, I'm just going to subtract 3 from both sides. And x is greater than or equal to negative 3. That would be our restriction in our domain. To figure out our restriction for our range, we plug that back in. If we plug in 3 for x, that means our output is going to be, negative 3 for x. Radical 3, or square root of 3 plus 3 is 0, and the square root of 0 is 0. 0 plus, or times 2 is still 0, plus 5 is going to be equal to 5. Now, if x is greater than or equal to negative 3, g of x will actually be greater than or equal to 5, whatever that value was for the k. Sketching our graph, we'll just make a table. And our table will be consistent with our domain and our range. We're going to take our domain and plug that in first. We said when x was negative 3, our function had an output of 5. So if I go to negative 3, I'll go up to positive 5. Thinking of other numbers that we could plug in for x, let's go negative 2. If we plug in negative 2 for x, negative 2 plus 3 is 1. The square root of 1 is 1. 1 times 2 is 2, and 2 plus 5 goes all the way up to 7. At negative 2, we go up to 7. If we keep going, I'll pick another number. I'll pick a positive 1. And the reason I pick positive 1, 1 plus 3 on the inside would be 4. And the square root of 4 is 2. 2 times the outside 2 is 4. And 4 plus 5 brings us to 9. At 1, we go all the way up to 9. So we can see our graph is getting kind of tall pretty fast. Thinking of another number to plug in for x in the parentheses, or in the radical, another number that would make sense to plug in for x would go all the way over to 6. 6 plus 3 is 9, and that's a perfect square. The square root of 9 is 3. Multiply it by 2, we'd get 6. But then if I add 5, we go off our graph all the way to 11. At 6, we're going to go up to 11. So you can see that that graph is getting bigger from left to right. It's going to start where our domain and range are, and it'll continue up to the right and go up towards positive infinity. Notice it stretches vertically. It moved left 3 and up 5. Let's take a look at g of x and the rest of the notes for 5.3 tomorrow in class.